Traditional 3D facial rigging is a labor-intensive process. To create expressive faces, animators rely on manual keyframing and complex rigging systems to manipulate individual facial features. This manual workflow carries a significant time cost. Industry benchmarks show that rigging and adjusting a single complex facial frame typically requires approximately 20 minutes of manual labor. This slow production pipeline cannot function in environments that require real-time responsiveness, such as virtual reality or interactive gaming. To maintain user immersion in these applications, the system must update the character's mesh across dozens of facial expressions with minimal delay. A 2025 framework by Liao et al. Proposes a fully automated, algorithmic alternative to this traditional manual keyframing. The core architectural innovation integrates generative neural networks with predictive models to execute end-to-end landmark detection and rigging without human intervention. By utilizing this hybrid architecture, the system reduces rigging latency from the 20-minute manual benchmark to under 300 milliseconds. Industry demand for this performance is rising. Generative models like Kling AI already prioritize character-driven storytelling that maintains high consistency across multiple connected scenes. High-fidelity, real-time animation requires a specific, hybridized mathematical pipeline to bridge the gap between static rigging and live performance. The first layer of this animation stack uses convolutional neural networks, or CNNs, to perform spatial feature extraction and replace manual blend shape mapping. The process begins by isolating the face region from raw input data, using standard algorithmic cascades to focus the network's attention. As shown in this training pipeline, the CNN identifies specific facial landmarks. Within the trained model, it maps fine-grained details like the curvature of the lips, translating these spatial measurements into probabilities for the 7 basic emotions. This spatial extraction is highly precise. The system achieves a 94.2% precision rate during landmark detection. Validating the CNN through Euclidean aerometrics shows that the pixel deviation between predicted and ground truth landmarks remains under 2.3 pixels. This deterministic mapping creates a geometric baseline far more consistent than a human animator manually adjusting blend shapes. While CNNs provide physical geometry, anatomical accuracy alone is not enough to create the expressive performances required for animation. Effective cartoon animation relies on emotional exaggeration. To achieve narrative resonance, a character's features often must break strict anatomical rules. Human animators traditionally manage this by stretching meshes to create extreme expressions, such as widened eyes or an exaggerated frown. The automated pipeline solves this by integrating generative adversarial networks, or GANs. Through an adversarial training process, a generator pushes the 3D mesh to synthesize these high-impact emotional variants. This synthetic emotion dataset demonstrates the diverse facial animations the GAN produces. The generative model achieves significant geometric distortion, maximizing emotional impact. Even at these extremes, the underlying 3D wireframe mesh adapts accurately to maintain structural integrity. However, standalone GANs are prone to producing disjointed or unnatural artifacts when generating consecutive frames in a sequence. While GANs provide the necessary artistic extremes, they require a secondary mathematical bridge to ensure these expressions remain stable when put into motion. The pipeline utilizes variational autoencoders, or VAEs, to create smooth transitions between the GAN's extreme expressions. The VAE maps out a continuous latent space. By approximating the distribution of latent variables, the system draws a mathematical path between a neutral state and an exaggerated one, such as GAN exaggerated joy. Traveling along this latent space curve allows the 3D face to morph fluidly, preventing harsh snapping or unnatural visual artifacts during an emotional change. Beyond single transitions, the pipeline must also maintain long-term temporal consistency across an entire animated sequence. To handle these sequence dynamics, the architecture adds a layer of recurrent neural networks, or RNNs. The RNN uses hidden states to retain information from previous time steps. This internal memory informs the calculation of the current frame, ensuring the motion is contextually aligned with what came before. By retaining this data, the RNN prevents spatial jitter and ensures the character's emotional evolution remains consistent over time. In this combined architecture, the CNN locks the spatial geometry, while the RNN drives the temporal progression across frames. Together, the VAE and RNN act as a stabilization engine, converting raw generated extremes into usable sequential animation. The theoretical merits of this architecture depend entirely on its computational efficiency during real-world deployment. Evaluation shows the system is highly efficient, processing times dropping to 12 milliseconds for low-resolution inputs. Even with high-resolution 1024 by 1024 inputs, the system processes the 3D model in under 350 milliseconds. Testing the architecture under concurrent load is necessary to determine its viability for multi-user environments, like VR or live social platforms. This data tracks total processing time against the number of simultaneous users. At 20 simultaneous users, the architecture maintains a total processing time of exactly 270 milliseconds. The CNN layer shows high stability with minimal increase in landmark detection time as user load grows. This deterministic scaling allows the pipeline to handle parallel workloads that linear, human-driven workflows cannot replicate. This automated stack enables 3D characters to move beyond the constraints of manual rigging, achieving the low-latency, high-consistency performance necessary for real-time interactive media.